Welcome to our last section of math analysis, critical points. It's the last thing that we're going to do to use derivatives to find what are called critical points. There's three types of critical points that we're going to be talking about. We have our relative local max and mins, and we have the point of inflection. Now the relative max and mins, these are things that we have already discussed in terms of when you're looking at a polynomial. It's that change that occurs, and actually what happens is it's the slope that changes. As it increases, the slope goes from positive to negative. So when that change occurs, that's where you have that relative max and min, when that slope goes from positive to negative or negative to positive. We also have something called an inflection point. The inflection point is when the concavity changes. So when you go, in this case, from concave down to concave up, there's a change. And so these are the three types of critical numbers or critical points that we will be looking at and identifying based off of our derivatives, and we'll talk about how we're going to do that. So there's really two things here. The first one we're going to look at, this is to find the possible extrema. So this is our max and min values. Well, if you think about that and you kind of go back to this picture, you know, what's happening at these points in terms of your tangent line? Well, your tangent line, it's just going to go straight across. And so when you look at that, well, what's the slope of that tangent line as it goes across? Well, the slope of that line is 0. So the slope of the tangent line is 0, and that's exactly what the derivative is. So what we're going to do to find these max and mins is we're going to find the point where the slope of the tangent is equal to 0. And so to do that, we're going to find the first derivative. And at this point, that's all we've done is found the first derivative. Then we're going to set that derivative equal to 0. Why are we doing that? Why are we taking a derivative and setting it equal to 0? Well, remember, this is the slope. And so we know that at the max and min points, the tangent line is going to be a horizontal line. So we know the slope will be 0. And then the last thing on 3 is we're going to find the coordinates of that. So once we actually find that x value, we will plug those back in to figure out what the y value is as well. So that's how we're going to find the relative max and mins. The second part here is for points of inflection. So points of inflection, we're actually going to find the second derivative. Some of you guys have asked me about this as we've been working on this, as to when we stop in terms of finding derivatives. Well, you actually can find your first derivative, and then you can turn around and find the derivative of that, and that's called your second derivative. So you can see how it's f double prime of x for the second derivative. Once again, we're going to set this equal to 0, and we're going to solve for that point of inflection. Once again, finding the coordinates by plugging the x value back in and solving for y. So those are kind of the things that we're going to be looking at, but let's kind of jump into our first example here as to be able to actually find these things. So find the critical point. So here's a cubic function. We want to figure out the critical points here. So what we're going to look at is we're going to look at the first derivative. So we're going to find the first derivative of the function. So this would be 9x squared using our derivative rules minus 36x plus 0. And so this, remember, represents the slope formula. Well, typically what we would do, and I'm going to erase this, but typically I'd say, okay, find the slope at x equals 1. And you would plug that in to find the slope. Now it's kind of backwards. Now we actually know what the slope is, because when we're looking for these relative max and mins, we know that the change in the slope goes from positive, as you're going this way it's positive, and then as you get past it you're going down, which is negative. So you know there's a change in the slope value there. And what happens at that point? Well, it's a horizontal line, so you're looking for the slope to be 0. So what we'll do is we'll say, okay, we actually know what the slope is. The slope is 0. And if the slope is 0, how do you solve for the x value? Well, now you're into solving polynomials, and this one's a quadratic, so looks like we can take out a GCF of 9x, and that'll leave us with x minus 4. So we get two possibilities. We get x equals 0, and we get x equals 4. And so how do you find these values? Well, once you now know what x is, to find the y value, you plug it back into the function. Okay, not the derivative, The derivative we already used to find the slope. Now we just want to find the y value. So we want to know what 0 comma this is and 4 comma that. So we're going to plug these back into the function. So we'll do f of, sorry about that, we'll do f of 0, and if you plug that back in, you'll get 3 times 0 cubed minus 18 times 0 squared minus 4. So you can see with all those zeros, everything cancels out except for the negative 4. So we got 0 comma negative 4. So that's one critical point. And then we'll also plug in f of 4. So that's 3 times 4 cubed minus 18 times 4 squared minus 4. And you can plug that into your calculator, and I get a value of negative 100. So we've identified what these critical points are. Okay. And we got to check for a point of inflection. Now, just thinking about what a cubic looks like, we know it starts and ends in opposite directions. So we can have a relative max and min, and we can also have a change in concavity. So we can't just stop here. We've got to say, okay, well, is there a potential of having a point of inflection? So we'll now check for that, which means we find the second derivative of the function. And so the first derivative was 9x squared minus 36x. So now find the derivative of that. That would be 18x minus 36. And once again, for the second derivative, we set that value also slope equal to 0. So that's 0 equals 18x minus 36. And when you solve for this, you will get x equals 2. So our point of inflection is 2 comma some value. Once again, how do we find the output? Well, you just plug 2 into the original function. So that's 3 times 2 cubed minus 18 times 2 minus 4. And then that will give us a value of negative 52. And so that's your last part there, is finding that point of inflection. So on this particular problem, we had a relative max, a relative min, and a point of inflection. And so that's really this kind of, once again, the last part of the notes is we're looking for those critical points. So here's another example if you want to kind of pause and try this on your own. It's kind of really very similar to what we just did in terms of finding those critical points. So we'll start with finding the derivative. Alright. We're looking for the relative max and min, so we're going to plug 0 in for the slope, and then we're going to solve for that value of x. And once again, on this one, we look like we get x equals 0 and x equals 2. So that's where the points are located in terms of x, and then to find the y, we just plug these values back in. So we plug in f of 0, and if you did that, you would get 5. And then you would plug in f of 2, and if you did that, you would get 1. So here are our relative extrema, 0, 5, and 2, 1. And then once again, because it is cubic, there's a possibility that of a point of inflection. So we'll look at that by finding the second derivative. So we're finding the derivative of the first derivative. So that's 6x minus 6. Set it equal to 0. Oops. And it's just linear, so you can solve that pretty quickly. And you get x equals 1. So when x is 1, what is y? Well, you have to plug 1 back into the original function. So that's 1 cubed minus 3 times 1 squared plus 5. So that's 1 minus 3, negative 2 plus 5 is 3. And so your point of inflection is at 1 comma 3. And that's how you find the critical points. And this is not just true with polynomials, this is true with all functions. So I could give you a lot of different kind of possibilities in terms of finding this. So here's one more I want you to I want you to look at. It's a little different than the first two that we just did, and it doesn't necessarily look like it in the beginning, but once you go ahead and kind of start working through this, you'll see why this one is slightly different. So once again, find the derivative. So that's 6x squared plus 12x plus 6. Set it equal to 0. This one there's a 6 in common, so I'm going to divide everything through by 6. Make it a little bit easier on me. And it looks like we can factor. And we get two solutions, but they happen to be the same. Well, if this is a cubic, how can I start and end in opposite directions and get only one relative max or min? Something doesn't seem right here. Let's go ahead and find what the y value is since we are here. So we'll plug f of -1 into the function, and you would get on this one -2, it looks like. So you can check me on that, but looks like we should get -2. But once again, let's just leave that for right now because we're not really sure what's happening there. Something doesn't seem right. Let's go ahead and do our point of inflection now also. So we'll find the second derivative. And that will give you 12x plus 12. Set that one equal to 0. And it looks like what you get is x equals -1. Well, we just had -1. So it can't be a relative extrema, max or min, and be a point of inflection. Which one is it? Well, remember, a cubic can also look like this. And so there is no max and min on this one. There's no relative max or min. There's only a change in concavity. And so actually the -1, -2, it is a critical point, but it is the point of inflection. It's not a relative max and min. Okay? So when you get kind of that second part, if it's the point of inflection, you might see that repeat there, but understanding that it's a point of inflection. So that's it in terms of finding the critical points. Okay, there's one more thing that I'm going to show you about kind of applying this idea of the derivative and what happens before and after the critical points. And here it is. And so let me kind of read through this as you're writing this down. But what we want to do is we want to determine if a critical number is a max min or a relative max, relative min, or a point of inflection. So I'm going to give you the critical point, and you got to determine which one of these three it is. Okay? But what we're going to do, instead of identifying what those are, we're going to look at values slightly smaller than x and slightly larger than x. And by doing that, what are we doing? Well, if you're looking at, let's just do a quadratic. If you're looking at the possibly relative max or min here, what happens to your slope? Well, as you get closer and closer to this point, your slope is positive. And then as you get to the other side of this point, what happens to your slope? It becomes negative. And so you're looking for that change from positive to negative to be able to figure out whether it's a relative max or min. So let's think about this. If I look at the derivative from the left hand side, that's a negative sign right there. If I look at the derivative to the left of x and it is greater than 0, so that's kind of the example I have right here. Let me erase it though. Alright, so from the right hand side, alright, as I'm looking at this, it's greater than 0, so my slope is positive. And then from the left, or from the right hand side, you got the derivative from the right hand side of x, it is now greater than 0, or sorry, less than 0. So now it goes down. So we go from a positive slope to a negative slope. Well, if it's a positive to a negative, what would that point represent? That would be your relative maximum. Okay? Whereas if you look the other way, if you look from the left and it's less than 0 to start off, so now it's negative, and then you pick a point to the right of x, and it's greater than 0, alright, now your derivative or your slope is positive. Well, what does that mean? If you go from a negative slope to a positive slope, then you're looking at a relative minimum. And so that's how we're going to identify what these critical points. And the last thing, in terms of the point of inflection, if you don't see a change in sign like that, then you look at the second derivative and you look at the left and you look at the right of x. And if the signs are different, then it's a point of inflection. If they're not different, then it's not a critical point. It's not a max-min or a point of inflection. So we're going to use this to kind of prove what these points are. So for example, on this last example here, determine if the points 1, -4 and 0, -2 are critical numbers, and if so, what type are they? Well, let's first start off with, okay, here's our function. Alright, what's the derivative? Well, the derivative of the function represents the slope, so this would be 3x squared minus 3. So what we want to do is to check to see whether this point 1, -4, move this down, and we're checking the point 1, -4. So as we check this, here's the slope formula, 3x squared minus 3. So what we're going to do is we're going to pick a value of x slightly to the left of 1. So let's just do 0.9. Okay, and we want to see what that slope is. And then we're going to pick a point slightly to the right of 1. We can do 1.1. And we want to look at those slope values. And this is going to help us determine if it is a going from positive to negative, or negative to positive, or neither. So if you plug in 0.9 into the derivative, okay, right here, we're plugging it into the derivative. That's going to tell us the slope at 0.9. So if we plug this in, I get negative 0.57. Okay, so right now, before 1, it's going down. At 1.1, the slope is 0.63. So now, after 1, it's going up. Well, if that's the case, then what's happening? That means that the point 1, -4 would be a relative minimum value, because the slope is going from negative to positive. And that's how you kind of prove or show that it is a minimum. Alright, so if you want to try the next one on your own, we have one more that we're going to look at, and that's going to be the point 0, -2. So once again, we've already identified the derivative. I'm going to write it down again, 3x squared minus 3. We're going to pick a point slightly to the left of the x value, which is 0. Sorry about that. And so we're going to pick, at 0, we'll just do negative 0.1. We'll figure out what the slope is there. We'll also figure out the slope on the right hand side of 0, which is 0.1. We'll work for that. And so when I calculated these, I came up with negative 2.97 and negative 2.97. So we don't have a change. We're going negative and then negative. So that doesn't tell us it's a max or min. It's neither of those two. So then we have to do the last thing, is to look at the second derivative. So maybe it's a point of inflection. So the second derivative of 3x squared minus 3 would be 6x, and that's it. That's all we have left, it looks like. And so now we'll do the same thing. We'll pick a point slightly to the left of 0 and slightly to the right. Plug those into the second derivative, and what we come up with is negative 0.6 and positive 0.6. So what are we looking for with the point of inflection? We're looking for different signs. So if we get different signs, which that's a negative, that's a positive, we did. Therefore, the point 0, -2 would be a point of inflection. And there you go. So that's how you can prove as to how or what these points are by using the slope and the first derivative and the second derivative. So that is it in terms of the critical points and the derivatives. So this is the last day of notes for you guys in math analysis. So I will be signing off. You guys have a good rest of the semester, and good luck on your test and your final exams.